Hello viewers, in today's class we are going to discuss one important concept from coordinate geometry under the topic conic sections, right? So here we'll see the concept of director circle of ellipse, right? So here we'll derive the equation of the director circle of an ellipse, right? So let us first see what is the meaning of director circle of ellipse. So now let us first consider a rough diagram of an ellipse, right? So here we'll consider a standard ellipse, right? Whose center lies on the origin of the coordinate axis, right? So here we have the ellipse, right? So here O is the origin of this coordinate system, which is also the center of this ellipse. So here the equation of the ellipse can be written as x square over a square plus y square over b square is equal to 1, right? So here if we take this point as a1 and this point as a2, this is the major axis, and if we take this point as b1 and this point as b2, then this is the minor axis, right? And here we have the two foci, and here we have f1 and here we have f2, right? And the coordinates are c comma 0 here. This is the standard notation, and here we have minus c comma 0. Here we have a comma 0, and here we have minus a comma 0. This is 0 comma b, and here we have 0 comma minus b, right? So this is the situation for the ellipse, whose standard equation is x square over a square plus y square over b square is equal to 1, right? So now what we will do, we'll define the director circle of this ellipse, right? So let us see how we can define the director circle of ellipse. So now before coming to director circle of ellipse, let us consider the concept of a tangent line to ellipse, right? So here we'll see the concept of tangency of any line at any point on the ellipse, right? So here we'll consider the line y is equal to mx plus c, right? So before coming to the concept of director circle of ellipse, let us consider the condition when this line y is equal to mx plus c is tangent to this ellipse, right? So now if this line y is equal to mx plus c is tangent to this ellipse, say at this point, right? Then we can draw the tangent like this. So this is a very important concept to discuss the concept of director circle, right? So here this is the tangent line. This line is tangent to this ellipse. So the condition for the tangency is given by c square is equal to a square m square plus b square, right? So this line y is equal to mx plus c is tangent to this ellipse when c square is equal to a square times m square plus b square, where c is the y-intercept and a and b are the semi-major axis and semi-minor axis, and m is the slope of this line. So the condition of tangency of this line to this ellipse is c square equal to a square m square plus b square. So here we are not going to derive this condition. So we'll take c is equal to plus minus square root of a square m square plus b square, right? Now if we substitute this value of c in this equation, then the equation of the tangent line is given by equation of tangent line is given by y is equal to mx plus minus square root of a square m square plus b square, right? So this is the equation of tangent line to this ellipse, right? So now here we see that we have two equations, right? We have two tangent lines. So one is corresponding to the positive sign and the other is corresponding to the negative sign, right? So we have two tangent lines. Now let us consider one more tangent here. Suppose here we have the point and the line is tangent to this ellipse. So let us draw the second tangent here, right? So the second tangent goes like this. This is a rough diagram. So here we have the second tangent, right? So now here we have two tangent lines on the ellipse. So viewers, now here comes the concept of director circle of ellipse, right? So what we have initially, we have an ellipse whose equation is given by x square over a square plus y square over b square is equal to 1. And we have a line whose equation is y is equal to mx plus c, right? Now this line is tangent to this line when we have this condition, right? So from here we have got two values of c, right? One corresponds to the positive value and other corresponds to the negative value, right? So when we substitute this value of c in equation 1, we got this equation. So this is the equation of the tangent line, right? So from here we have got two tangent lines, right? So this is the first one and this is the second one, right? So now here comes the concept of director circle of ellipse. Now see, if these two tangents are perpendicular to each other, right? Suppose this angle is 90 degree. Now suppose these two tangent lines intersect at 90 degrees. So this angle is 90 degrees. So what is a director circle? So the director circle is the locus of the points of intersection of tangent lines which intersect at 90 degrees. So in other words, we can also say that the locus of the points of intersection of the tangents to this ellipse which are perpendicular to each other is called director circle, right? So whenever we have tangents which are perpendicular to each other, then the locus of their point of intersection traces a circle known as director circle. Now let us consider two more points in which we have the tangent lines, right? Suppose here we have a point. Now let us draw the tangent line like this, right? So this is the tangent line, right? And suppose here we have one more point. Now let us draw another tangent line, right? So now if we produce these two tangents, then we get the point of intersection like this, right? So here we have the point of intersection. Now see, if these two tangents are perpendicular to each other, right? So here we have to take note of this, that if these two tangents intersect at 90 degrees, then this point is the part of the director circle of ellipse, right? Or the locus of this point is the director circle of the ellipse. So here also we have got the point at which these two tangents are perpendicular to each other, right? And suppose here also we got the point of intersection where the two tangents intersect at 90 degrees, then these points these points lie on the circumference of the director circle of the ellipse, right? Now let us redraw this diagram. So here we have the ellipse and here we have this point of intersection of these two tangents which are at 90 degrees. So here we can take this point as L, right? So let us draw or let us locate the point L here, and here we have another point. Say we can write this point as M, and this point M is the intersection of these two tangents at 90 degrees. So here we can locate the point M, right? So now if we join, or if we draw a circle like this, so this is not an exact circle, but here this circle is known as the director circle of this ellipse. So viewers, this is the director circle of this ellipse, right? And the points L and M are over the circle. And here one important thing is that the center of the ellipse is the origin, that is 0 comma 0, right? So the center of the director circle is also 0 comma 0, that is the origin. So let us revise the definition of the director circle of an ellipse. The director circle of an ellipse is defined as the locus of the point of intersection of the tangents to this ellipse, which are perpendicular to each other, right? So now let us derive the equation of the director circle, right? So for this, what we will do, we'll take the coordinates of this point L as h comma k, right? So we know that the director circle of an ellipse is the locus of all the points which are the points of intersection of tangents to the ellipse at 90 degrees, right? So now this point L has the coordinates h comma k, right? And if we draw a tangent to the ellipse at or from this point, then we see that the point h comma k, it lies on this tangent, right? So this point h comma k must satisfy the equation of the tangent, right? Because the equation of the tangent line to the ellipse is given by this equation. And if we take this point L as h comma k, then this tangent line contains this point h comma k, right? So this point h comma k satisfies this equation. So now if we take, or if we replace y by k and x by h, then we'll get k is equal to mh plus minus square root of a square m square plus b square, right? So now let us simplify this equation. Taking this quantity to this side, we'll get k minus mh, and then squaring both sides, we'll get here a square m square plus b square, right? So here we have a minus b whole square, so this can be written as k square plus m square h square minus 2k mh, and this is a square m square plus b square, right? So now we can frame a quadratic equation in m, right? So now if we take this quantity to this side, then we'll get h square minus a square, and here we have m square, and here we have minus 2k mh, and taking this b square to this side, we'll get k square minus b square is equal to 0. So now we have a quadratic equation in m. So this is of this form, that is am square plus bm plus c is equal to 0, right? So this is the standard form of the quadratic equation. So now if we compare this equation with this one, so we have a is equal to h square minus a square, b is minus 2km 2kh, and c is equal to k square minus b square. So now since this equation is quadratic in m, so this quadratic equation must have two roots, right? So the two roots may be denoted by m1 and m2, right? And these two roots m1 and m2 represents the slope of the two tangents which intersect at right angles, right? So this is an important thing here, right? So see, here we have the first tangent which is shown by this green line, and the second tangent is shown by this blue line, right? So m1 corresponds to this green line, and m2 corresponds to this blue line. And similarly, when we take these two tangents, then m1 may correspond to this tangent or this tangent, and m2 may correspond to this tangent or this tangent, right? So we have a quadratic equation in M which has two roots denoted by m1 and m2, and m1 and m2 represents the slope of the tangents to the ellipse which intersect at 90 degrees, right? So here let us quickly revise a concept from quadratic equation, right? See, in quadratic equation we have seen that if we have an equation of the type ax square plus bx plus c is equal to 0, and if it has two roots alpha and beta, then the product of the roots is given by c over a, and the sum of the roots is given by minus b over a, right? So this is the concept which we have learned in our previous classes, right? So here I will use this concept here, right? So now here this quadratic equation has two roots m1 and m2. m1 may be taken as alpha and m2 may be taken as beta, right? So the product of the roots, that is alpha beta, so here we have m1 times m2, right? So the product of the roots is given by c over a. So here we have, this is c, so we have k square minus b square, and a is h square minus a square, right? So now we have the product of the roots as k square minus b square over h square minus a square, right? And we have just said that m1 and m2 represents the slope of these two tangent lines which intersect at 90 degrees, right? So we know from trigonometry or from straight lines that if two lines intersect at 90 degrees, then the product of their slopes must be equal to minus 1, right? So two lines are perpendicular when the product of their slopes is equal to minus 1. So here we can write minus 1. So we have minus 1 is equal to k square minus b square divided by h square minus a square. So now we can take this term to this side. So here we multiply h square minus a square by minus 1. So we have a square minus h square, that is equal to k square minus b square. And now if we rearrange this equation, then we get h square plus k square is equal to a square plus b square, right? So this is the equation of the director circle, right? We'll express it in terms of x and y. See, here we have taken the coordinates of any point lying on the circle which is known as the director circle as h comma k, and here appears h and k, right? So the in general, the equation of the director circle may be written by replacing h by x and k by y, right? Because director circle is the locus of this point h comma k. So now replacing h by x and k by y, we get this equation x square plus y square is equal to a square plus b square, right? So the director circle or the equation of the director circle is given by this equation, which is the director circle of this ellipse. So viewers, this is how we can derive the equation of director circle of ellipse, right? So let us quickly see an example. Suppose we have the equation of an ellipse as x square over 16 plus y square over 9 is equal to 1, right? And we are to write the equation of the director circle of this ellipse. So what we will do, we'll compare this equation with this one. So we have a square is equal to 16 and b square is equal to 9, right? And we can simply substitute the value of a square and b square over here. So the director circle is given by x square plus y square is equal to 16 plus 9, that is x square plus y square is equal to 25. So this is 5 square, right? So from this equation we see that the radius of the director circle is given by 5, right? And the center of the director circle, it lies at 0 comma 0, which is also the center of the ellipse, right? So this is how we can discuss this concept.